Welcome back to another night at Monte Carlo. Tonight we will be looking at simulations. So we've done science before on the computer, but we haven't yet done simulations. So this is somewhat different, somewhat a higher level. And to explain what it means, let's get on with it, okay? So these are the real things we'll be doing now, real science. So we have two problems we'll look at. And each one gets more and more interesting, I think, but also they're both serious, real scientific problems. These techniques essentially are used in modern day research, a little more sophisticated maybe than we're doing, but very similar. So the first problem we have here is discussing random walks in science. And random walks occur all the time in nature around you. You've probably had the occasion of, some woman walks into a room with beautiful perfume on, or some guy with too much aftershave, and suddenly the whole room just fills up with that smell. And it may only be a few molecules or atoms or a few hundred being given off, but it makes its way to you very quickly. Well, that's a random walk of molecules. Electron transport. Wires, current. Anytime electricity flows in through wires, it's not flowing in direct lines, it's actually a random walk. So this kind of an issue has many, many applications. Here you see, lit up on the screen, diffusion limited aggregation. It's an applet we're about to show you. And these applets are available from links on the web page for this course. Maybe on the CD you'll find also appropriate links to these applets, and it may work for you. Diffusion limited aggregation is just a complicated way of saying it's another variation of a random walk. Here it's one in which we show how diffusion can limit the speed at which things walk through nature, and they can clump together. So let's see if we can get this to work and look at the applet. You can do this on your own. Aha, here's the applet. So this is part of a applet collection available in English and Spanish by a good colleague of mine, Manuel Paez, and his research group at the Universidad de Antioquia in Medellin. Okay? So here's an applet. What you see in the middle is a little red dot, and what you see on the outside is a blue circle. And we're going to start off random walkers. So this is a simulation of real random walk. And when the walkers get to the middle, the red dot, they'll stop. And this is aggregation. This might be a model of how stalagmites, stalactites form. Okay, so let's start it. Have to push the right button. And there you see a random walk occurring. Okay, and there's several random walkers here, and they're building up in the middle. The red dot is getting larger because that's the stalagmite forming, or that's the aggregate forming. So this is like a rock formation, but a random process, and you can see these walks occurring. So you're free to play with this on your own. You can stop it. It's really interactive. You can reset it. We can have many more walkers going at the same time. Here we can, let's say, 20 or 30, and you'll see many walks going on. You'll see the little rock stone in the center growing a little more quickly. Okay, so we'll stop this, and now let's get back to what we were talking about. Okay, so what's the problem at hand? The problem at hand is how far does a random particle move after making n steps? Okay. So let's say we have a gas molecule. It makes n collisions, each one random. In other words, didn't know where it came from, it doesn't know where it's going. It makes a random collision, any directions possible, and how far does it get from the origin after n steps? So we'll say here, we'll say we have n collisions the atom is making, and we think it travels a distance r. And in the picture, what we're showing you here is actually results of simulation, and each color represents a different walk. So this is to give you an idea of, well, the most natural thing, at least a very natural and logical thing to say is, if it's just making a bunch of banging its head against the wall, collisions, one to the right, left, up, down, it probably doesn't get any place. If it's as likely to go to the right as it is to go to the left, then probably never gets away from the origin. And what you see here is, for all the different walks, it's true, if we averaged over all the walks, the mean distance from the origin, it would be back at the origin. But for any one walk, for example, let's look at the red walk, it bounces around all directions, but eventually it gets away from the origin, some finite distance. Likewise here for the yellow walk, it moves all around, but it gets away. The green to, well, whatever color that is, mauve, the blue, they all get away from the origin. And you see, on the average, and if you do thousands or millions of walks, they're covering the whole 4 quadrants, so it will average out to 0 as far as location. But the distance traveled, how far any one walk goes, a scalar number rather than a vector number, is different. We can add that together. So that's our problem. We'll see more pictures make it clearer. How do we do this? Well, what we say is, let's imagine a model. It's a simple model, but it's not a bad model. So let's imagine a model in which we have our walkers starting at the origin here and making n steps. So here's the first step, direct step 1. The second step is 2. It's supposed to be random directions, but they're not quite random because I'm trying to fit it on the page. Okay. Step 3 here, step 4, and eventually, after capital N steps, it's a distance r from the origin. That's our model. Okay. And the algorithm we use, the computer program, is called a walker, or a random walker, and it's used for everything in nature. It's used for modeling high-energy experiments, it's used for modeling electronic apparatus. It's a very basic technique. Okay. So, what about the theory? Now, we don't have to do the theory. We can just do the simulation, as we've indicated on the previous slide. But we're going to do the theory now anyway to have something to compare to. And, you know, when I was growing up in science, all we had was the theory. We didn't have any simulations to look at, and it's in all the books. And the question is, how do you describe this problem mathematically? Okay? So here, let's look at this slide a second. Okay. And here now is the same diagram repeated. Here's our random walker, and the only difference is we're going to end up still distance r away, but I've indicated for the first 2 steps that step 1 has a certain delta x1 and a certain delta y1. That's the distance covered in the x direction and the y direction. Step 2 has another certain distance, delta x1. And what's obvious here, if you look at the diagram, is, okay, after n steps, all of the x displacements add together algebraically. They can be positive or negative, but for any one walk of n steps, they're not going to average to 0, they'll average to some number. And all the steps, the component of the steps in the y direction add together, if you want algebraically or vectorially. So what we're doing is we're just doing a vector sum. So we say, okay, I know how to calculate that distance, r. Well, at least I know how to calculate the distance r squared. That's just the magnitude or the length squared of the vector r. I add together all the delta x's for all the steps, for n steps. I square that, and then I add together all the delta y's, and I just use the symbol here, replace x by y. I add that and I square it. So that's what I do in equation 1. And then in equation 2, I just expand it, except I leave off some of the terms. So you get a delta x1 squared, you get a delta x2 squared, all the way up to delta x sub n squared. Those are all the x. Then you get all the cross terms, 2 delta x1, delta x2, plus 2 delta x1 times delta x3, etc. And then you get the same thing with all the x and y's interchanged. Okay? So all the cross terms, the only interference you get is in delta x's, and delta y's amongst themselves. The x's and the y's don't intermix. Okay? So that's an equation that's exact. And as most things exact, it's pretty useless for doing the calculation. But here's what we're imagining. We're imagining, number 1, that we have many, many steps involved. And number 2, that they're random. They're in all directions. So we could say, if we have a large, large number of steps, and they're in random directions, something happens. Okay? That, sometimes they go one way or another. And if we take the average over many of these simulations, then we should end up with a bunch of terms canceling. So let's see. What we say here explicitly is, okay, if the steps are random, then delta x1 and delta x2 can be positive or negative, so all the cross terms could be positive or negative. It'll be both. But delta x1 squared is always a positive number, just like delta x sub n squared, delta y sub 1 squared. They're always positive. So the positive numbers, when we average, remain positive. The other terms, the cross terms, occur with equal likelihood of positive and negative signs, and so they cancel out. So what we can say is, approximately, if you have a large number of terms, a large number of steps, the average value of r squared is going to be delta x1 squared plus delta xn2 squared, etc. The same with the y's, as we have in equation 3, where I've written in the y's this time. But then there's just how many terms? There's n delta x1 squared and delta y1 squared. But we know for each step, as we've drawn it here, has a certain length. We call it small r. So that we just add these n terms together. Each one has the same value. So we get r squared is equal to n times the small step size squared for each step. Okay? So that's the average, if you want. That's the average of the mean squared. That's r squared. If we now take the square root, we say the root mean squared difference. In other words, this root, because it's the square root, mean squared because we've taken the mean of the square. So the root mean squared distance, we predict theoretically, is going to increase like the capital N, the square root of capital N, times the size of each step. Okay? So that says, we show here on the diagram, that says that on the average, the distance squared, or the square root of the distance, so it's not the location, not the vector location, because on the average that's at the origin, but the average distance covered should increase like the square root of n. And the way you check this out in simulations, as we've done here, is we draw a graph of the distance r versus the square root of n. And the theory tells us that it should be a nice straight line, as you see here in red dashes down the middle. And it's a simulation, and one of the reasons we're computational scientists is we'd like to experiment. If we experiment here with different kinds of ways of putting in randomness into the calculation, putting it in minimally, putting it in maximally, we see that we get different answers, but the simulations, which agree, well, for small n we don't see the difference, they agree on the average to the theory, depending just how we do it, and they oscillate about that, which is what you'd expect. It's statistical, and in nature, if you did this measurement in nature, you would not expect exact agreement either, because it's random. There's chance involved. Okay. So, we've said a lot. The hard part's over. Now the fun begins. So now let's do a laboratory experiment. I said on the beginning slide that we're going to do simulations. And what a simulation means is we're going to take the equations of nature and an algorithm and try to reproduce them on the computer and have a virtual laboratory. So have the computer act as if it was nature. So not just use the computer to calculate something, but use the computer to simulate nature. So this is the first time we've done that. That's why these are called simulations. Some people call most everything done on the computer simulation because it never does it exactly the same as you might by hand. But these are really what we mean by simulation. When we go to nature and we try to repeat it on the computer as nature does. And the questions always arise, if it works, is this a good description of nature? And the answer is, well, if it looks like nature, and if this is how we think nature works, it probably is how nature's working. Okay, so here we have the first simulation, and now we need to talk about the algorithm, how we apply this theory, how we apply then the model, just the walkers to go, and how we reproduce the graph just as this. Okay, so we want you to go into the laboratory now, write a simple code that does a simulation of this. You can probably find one on the CD that we've given you as a model, but I recommend you do not run that, but you just write your own. You can look at that for help, because you need to know what's going on, and there's not a tricky point, but there is some important points. Okay? What we want to do is, number one, see if the root mean squared distance goes like the square root of n. It's proportional to square root of n. The essential part in point one here is what we take the average of, that's what these brackets mean, is not r, but r squared. So you only take the average of the distance squared. You never take the average of r, because you'll get a different answer. The theory corresponds to the average of r squared. So we want to do that. What we need to do in order for the simulation to work, to be as close to the theory as we derived it, is to have all those terms cancel. And the only way to have those terms cancel is to build in as much randomness as possible. And while we said that one way of doing this is to imagine that the angle at which the walker takes each step is random, we found in practice, and you're welcome to find a better way, that we just treat each delta x as a random variable and each delta y as another random variable, and then we built in, unrelated to each other, we build in even more randomness into the process, and that helps get the expected results more quickly. But as this is experiment, this is science. It's not obvious what the answer will be. We have to do the experiments. That's what we do it for. Then as a practical matter, if we're going to vary, as we say on step 3 here, delta x and delta y with random numbers, well, random numbers will generate them in the range from -1 to +1. Notice here we're scaling them. Usually we said the built-in random number generators vary between 0 and 1. But we want delta x and delta y to be both positive and negative in order to get the cancellations that the theory has. So we'll have delta x and delta y each in the range -1 to +1. So it's just a simple scaling. But then in order to remove the actual size of the step, or to take into account the fact that if we're letting delta x and delta y be random, then the length of each step might be random. And you should get very similar results even if you include that, but I don't know, students seem to feel more comfortable saying, but shouldn't the steps be constant? Okay, so we'll make the steps constant. So we'll normalize, as the term goes. We'll normalize each step, as we have in equation 1 and 2 here, so that each step has length 1. How do we do that? Well, we do that by just picking delta x and delta y in the range -1 to +1. So here I call it delta x prime. So the primes mean the previous version. And then we just divide the step, delta x, by 1 over L, where L is the length of the step, the original length of the step, which we just calculate. That's just the square root of delta x prime squared plus delta y prime squared. So you form a step, you determine its length by taking the square root of the distances, x's and y's, and then you just divide that by 1 over L, then you get a new step of length 1. Okay. So what do you have to do? So what you have to do now is plot, as we show on the figure here, not just one walk, but you want to plot a number of independent walks. Why is independent underlined? Well, because we're saying you just can't run the program n times and get different walks. It's going to start with the same seed each time, so you need to make them independent by having a different seed each time. Okay, so the different colors correspond to different seeds, and that's enough to set you off on wild paths. 1,000 steps is a good number to start with, just to see what happens. Gives it enough chance. And then you need to look at these, as we have the figure here, and decide, is this random? Do these look random? Students, when we first started teaching this, would come up to me and say, is this right? Is this what a random walk looks like? And the answer is, well, only Mother Nature knows what a random walk looks like. I've never seen one. All I've ever seen is a simulation. Now I've seen enough of them to believe them, but this is what it's like. Okay. So now let's look at some of the details we have to go through on the next slide. So take a look at this, and we'll go through some of the specifics. Okay. The critical thing in doing a simulation with random numbers is that we have as much randomness as possible. And we have to have good statistics so that we know we agree with the theory and that we've averaged out some of the statistical variations. Good statistics almost always means having good numbers. Now, we should also have good theory and good programming techniques so we don't have systematic errors. But what we're trying to eliminate here is not the systematic errors, but the random errors. Okay? So let's say capital N is the number of steps we make in a single trial. And we can run various trials, each with different seeds. Now we do something new. We say, in order to get the averaging to work, we need to have various trials. So the word trials is used to mean we also run the simulation independently. Each independent run is called a trial. And we want to average then over many different trials. At some point, in order to get the graph we talked about where we look at how the distance varies as the square root of n, we're going to have to change n. But for this case, and for each n, keeping n fixed, we have to go through many trials. And a good rule of thumb is to say we want the number of trials, capital K, to be something like the square root of n, where n is the number of steps. So to repeat, for n fixed, we go through roughly the square root of n trials. Then we change n, and we keep track of all the results, and we do it again to get the n dependence. We have to do many trials for each value of n. The critical thing here is for any one value of n, we have to calculate the average value of r squared. So we do that for small k here represents k equals each trial number. So trial 1 we get a value of r squared, capital R squared. Same thing for trial 2, and we keep track of those. Then we calculate the average, or we calculate the mean square. Okay? So R squared is 1 over k. K is the number of trials, and the sum of R squared for all the trials. Okay? So this averages out some of the statistical deviations that we get. And then only when we're all done on equation 3 here do we take the square root. So, repeat, you don't take the square root up here and then take the average of the square roots. You get a number, but it's not, you don't get all the cancellation we want. Okay. So now then we try to do a curve, make the curve like we have here. We want to plot r, which is the root mean squared distance, versus the square root of n. And what we expect here is that for small n, it doesn't matter very much if the theory agrees or disagrees because we don't expect statistics to be good. For large n, we expect statistics to be much better. And as you see here, the theory's in red. Let's look at black, which has the good x and y random. You see it's above the theory, then it's below, then it's above. Is that right or is that wrong? Well, we expect to have deviations like the square root of n. Because for n steps, so this would be the square root of n, because that's what we're looking at. And as n gets larger and larger, we expect the deviations to get larger. Okay. Relative, percentage error should be something like 1 over the square root of n. But the actual error itself, should get larger, but it should deviate around the curve. That's what we expect. And then for you to do, point 12 here is figure out what n value is needed in order to get 2 or 3 places agreement in the relative error. Always in the relative error. Okay. So now I suggest you take a break. Go into the laboratory and try the random walk simulation. Because now we have, after that, we have another simulation very similar. So, go take a break, and then we'll come back, and we'll be here when you come back. Well, welcome back. I hope you enjoyed your random walk through nature. And now let's do something else, random as well, and we'll be spontaneous. Spontaneity is nice in life, right? Let's talk about a really subtle problem, but a fascinating one and an easy one, spontaneous decay. And I must admit, I've gotten into arguments with people, experts in radioactive decay, about this experiment, this simulation we're doing. And they think they're experts in the phenomenology, and they probably don't quite understand what the law of nature is here and what the basic theoretical understanding is. So, if you don't agree with me, don't worry about it, I'm right. But let's talk about the basic fact of nature. What do we have? The basic fact of nature here is that radioactive decay or spontaneous decay is a natural process. And what we try to do as scientists and as physicists is we try not to explain why natural processes occur as much as to describe them in the simplest way possible. That's what we're trying to do. We then may go down, and we'll talk about it, why something's happening at a better level, but it's still ultimately just a description not an explanation of why. Why is for philosophers. So, we'll talk about how nuclei and atoms decay. Atoms decay up here in fluorescent light bulbs. Fluorescence is a spontaneous decay of atoms. Okay? So, radioactivity, as you hear the Geiger counter, is spontaneous decay. We use the term, item 3 here, spontaneous. What does that mean? Okay. Well, spontaneous means something that happens on its own, something that doesn't require external stimulation. You're not responding to some clue. It just happens on its own. It's hard to believe, and many people maybe don't understand, that a process in nature has been occurring since the universe was created that's spontaneous. Radioactive decay is one of those. It just happens. It happens all the time around us. It's not because we've made power plants, but nature has spontaneous decay of radioactive materials. Okay? In fancy terms, item 4 here, we call it transmutation. Usually it's called transmutations of the elements. So this is what happens in a nucleus. For example, a uranium nucleus sitting by itself in the ground, in a mine someplace, in a rock, will give off alpha particles and end up with a thorium nucleus. And so when this process occurs, when radioactivity occurs, the elements transmutate. They can't go back to what they were. They've changed. Okay. What do we mean by a random process here? When we say it's random and spontaneous, we mean it takes a certain amount of time to decay, half-life, or all to decay or to decrease in number. But just the exact time when a radioactive, unstable particle decays, we don't know. It's a spontaneous process. It happens on its own time scale whenever it wants. It also means we can't influence it because it's spontaneous. One of the reasons why it's so hard to deal with the waste from nuclear reactors is you'd say, well, why don't we just put them in a magnetic field and do something to them? Well, or speed up the decay so they don't decay over thousands of years and leave it to our grandchildren to worry about. Well, the answer is it's a spontaneous process. Nothing we can do from the outside, short of sending another high-energy particle in and breaking up the nucleus, nothing we can do from the outside will change that process. Okay? So it's both a sophisticated process and it's independent of what we do. It's independent of how many other atoms are nearby it, to a good approximation, other than when you build a bomb and then you put enough atoms closer together they begin to influence each other, but we won't get into that. So, in the box here on slide 7, our single equation is a way of summarizing as best we can nature, how we can describe nature. And it says if we have a radioactive bunch of atoms here in one place, the probability of any one of those atoms decaying per unit time, okay, so that's what we're dividing by T, particle probability of decaying per unit time per particle. So for each individual particle, the probability of it decaying in any one time interval is a constant. That's the law of nature. It means it's a constant. It's independent of what time it is. It's independent of whether it's decayed before. Well, obviously if it decayed before, it can't decay again, but it's independent of whether some other particles decayed or how many neighbors it has. It's always a constant. The minus sign is here just to indicate that it's negative. It always decreases in number. So the number of particles always decreases. So if we look at the number of particles as a function of time, they always go down. They always decay. If we look at the activity, which is the rate of change, it also goes down in time. Why is that? Well, because if there's fewer particles, then there's fewer around, there's fewer particles to decay, and the rate at which they decay decreases. These two are just proportional with each other. So that's the basic law of nature. Okay? So what is your problem? What's the problem with you anyway? I don't know. The problem with you is you have to do a simulation. This is your problem. Okay? So we want to simulate how various numbers of nuclei, let's call them, decay in time. Okay? We'll get a bag full of nuclei together, put them here, and say, how do they decay in time? Now on the computer, the radioactivity is not going to hurt. And the point which I get into arguments with is to say, does it ever look like exponential decay? And the experts in the field will often say, hey, radioactive particles, if left alone, will always decay exponentially. And the answer is, well, no, if they always decay exponentially, at some point there's just a few of them left, and then it sounds like a Geiger counter. It sounds stochastic, in other words, a process which has randomness, chance involved. Some decay, some don't. And then it's not exponential. And probably never is exponential. It's always a random process. It's just if so many happen at one time, it sounds continuous, sounds exponential. We'll talk about that some more and give the mathematical. And then for you to decide, and I've told you what you need to decide if you want to get an A in the course, which is the simulation exponential or is it ever stochastic, and which is a more accurate description of nature? So as we have in the box here, the law of nature is that the number of particles decaying per unit time per particle is a constant. Okay. So we try to write that down in more mathematical form so that we can develop an algorithm which would be appropriate. The algorithm is very simple. So what this says is, let's take a time interval delta t. 1 second is fine. Think of delta t. In 1 second, delta n is the number of atoms which decay. Fine. If we divide that number of atoms which decay in 1 second by the number of atoms we have in our bag for that 1 second, divide that by delta t, 1 second, we get a constant. Okay? So that's one of the things. We want a simulation. We want to look at this number, delta n divided by n, delta t. That'll be a constant. If we also look at the activity, the number of decaying per unit time, that's minus lambda n sub t. That's called the activity. And obviously, if it's proportional, it's going to look just like n of t. So that's the mathematics. Now here's the simulation. So take a look now at slide 9, and then we'll look at a bunch of things. Okay. How do we simulate this? Well, here's the basic algorithm, right at the top. And on the bottom we have sort of a little more than pseudocode, actually how we would write this down, because it may not seem clear, but let's look at the algorithm. Algorithm says we have our bag of nuclei right here, and we loop through all the nuclei which remain. We can't, if there's 1,000, 10,000, we loop, we just we make a query. For nuclei I, will it decay? We have to make a decision. How do we make that decision? Well, we generate a random number, r sub I, and if the random number is less than lambda, that's the decay rate, which we've written down before, it's a constant. If the number is less than lambda, if the answer is yes, it decays. That's the algorithm. Simple as that. How do I know it's less than? Well, if lambda is the decay rate, if we make lambda larger, think of it this way. When lambda gets larger, more atoms have to decay. Okay? So if more atoms decay, we should get yes more often as an answer. So that's how I know it's less than. If r sub I is less than lambda, and if random numbers say between 0 and 1, we make lambda some units set for time, so lambda is between 0 and 1. Okay? So we don't even have to do anything. The larger we make lambda, more decays we get. That's how it goes. And then, after we've queried every single nucleus that remains alive, we say, let's go on to the next second. Let's t equals t plus delta t, record how many nuclei decay, how many are left, decrease the number left by how many decayed, and then just repeat the loop until nothing's left. What happens when you do this? Well, we've done this, and we've done the simulation, and if we take the results of the simulation and we convert them to sound, this is what you get. Why not? You get sound, which is not coming up now, so let's see, we'll do it another way. Well, it's not unusual for things on the computer not to work. We've touched it a little bit, we've made changes. So one of the good things about this is you have to learn how to fix problems on the computer. The best way is to go back, look at the program, see why it's not working. There's other approaches. Some people say a prayer. Some people knock on wood. Some people yell at the computer, come on, and try again. Whatever works for you, try it. So let's see. Let's see if it'll work now, please. work. So that's the Geiger counter sound. That's not a real Geiger counter that we've recorded. That's actually just a result of the simulation, which we've converted into ones and zeros, and then converted into sound. So if that sounds just like a real Geiger counter to you, that's indicating that the simulation down below here, which you can see the number of particles on a log scale versus time, you can see how it starts off linear, it starts off smooth. That's when the Geiger counter is boom, 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 boom. And then when you hear the stochastic, you're hearing that. So let's play that again. Exponential, and then obviously stochastic. Okay, how do we code this up? Yes, okay. So we have the sound recorded, but here we have as one of the applets that we've written. So they're available with the links from the CD again. Here we have a little Geiger counter simulation. So this is just a Java applet. So it just means that it's a program written in Java designed to run over the web. And it's not a big application, so it's a small application, an applet. Okay. So here we have our Geiger counter. And we can vary the number of atoms or particles or nuclei. Here let's make it 32, and here we can vary the decay rate up to 1, as I said, which in these units, 0, and I'll make it fairly slow. Gives me a chance to talk, and you know I love to talk. Okay, so here we have the simulation, and let's start it. And what you see here in red is all of the nuclei that are present. And then you see here in yellow, each time a nucleus decays, it turns yellow, and you hear a click. That's the Geiger counter. It's nice and slow. And what you see here in the black curve is an exponential. And so and if you look really closely here, if you have better eyes than I, you see a question mark, and that's each nucleus being queried. So the reason we've made the number of nuclei so small is just you can see the query. And you can see here, wonderful, it's a stochastic process. Notice how it's a bunch of histograms, but on the average, they do follow an exponential decay like. But it sounds somewhat like a Geiger counter. So let's reset this, boom, and now let's keep the number of atoms high, so it goes for a while. Let's make lambda a little faster, so they'll decay more quickly, and it won't be the same. You know, sometimes they'll decay quickly, sometimes 1 or 2 will last forever. It's a random process. And here you can hear them decaying more quickly. There's not going to be many left. They're really going at it. There's a small number, and a few of them are left, and it's gone. Okay? So you're welcome to play with this some more. It's a real simulation. Okay, so here's the algorithm. So down below here is the algorithm written down in pseudocode as you would have it in Java or C, very similar to what you'd have in Fortran. So the algorithm says, let's repeat a loop as long as, or while, the number of nuclei remaining is greater than 0. Okay? Actually, or equal, yeah, greater than 0. Because if it's equal to 0, we're done. So let's start off saying there's been no decays initially, and here's the loop. So it's a for loop. For I equals 1 to the number of nuclei remaining, ask the simple question, is the random number I choose less than the decay rate? And you can choose any number for lambda, as you should. If the answer is yes, then increase the number of decays, delta n, by 1. When you're done with the loop, increase the time by 1, decrease the number of nuclei which those have decayed, output this to a file, so you get a nice file, and then repeat the process again and again. Okay? And as you see here in the blue figure, pretty blue, robin eggshell blue figure, we've made a plot of the number of nuclei on a log scale remaining as a function of time. And what you see here is fascinating for many reasons. We start off with just 10 nuclei, then 100, 1,000, 10,000. That should be 100,000. And you see in all cases, it's almost like a straight line, because this is a semi-log plot. The slopes look the same. The slope is lambda. Lambda is the slope. It's a negative slope, minus lambda is the slope. And the slope doesn't change here. If you change lambda in the simulation, which you should do, what you'll get is a curve of a different slope. But other than that, the slope's independent of the number of initial atoms. And that for large numbers of atoms, it does look like an exponential, which is a pure straight line. But then if you look closely, you see, oh, there's always some variation occurring. And when the number of atoms gets small, down here, say 10 to the 2, which is about 100, you can see the fluctuations occurring. It becomes stochastic. So the answer to the question I gave you, is it stochastic? It's always stochastic, but it looks exponential when there's a large number. So actually, this one curve for 100,000 contains all the others in it as well, because it's a spontaneous process. It doesn't matter where it began, it's just going to continue. So let's end off now and say, okay, some of the mathematical types out there want to say, but it should be exponential decay. Why isn't it exponential decay? So look at slide 10 here, and we'll see how exponential decay is only an approximation to nature. Okay. Exponential decay occurs only in the limit. In the limit when we have very large numbers of particles, we have to let the number of nuclei go to infinity. We have to assume that we've made a time interval, not a second, although for some radioactive particles which have a lifetime of 10 to the 10th years, age of the universe, a second is probably a very small number. But mathematically we have to let the time interval go to 0 so that the number of particles decaying at any one time interval approaches 0 as well. So in that limit, where all of the steps become infinitesimally small, then we can approximate delta n by delta t by the derivative dn dt. And this, of course, is backwards from what you always see in your calculus class or your elementary physics class, where we start off with delta n delta t, and then we say when we do this mathematically exactly, we go to dn dt. In this case, nature always is a finite process because you only have a finite number of particles. Nature has the capital deltas, and the dn's only occurs approximation. So if we had that approximation where the number of particles is very large, the time interval infinitesimally small, then we get a differential equation describing it. And once we have a differential equation, we can solve the differential equation, we can integrate it, and then the solution would be equation 2. The number of particles at time t is equal to the number of particles at time 0 times e to the minus lambda t. That's wonderful. And lambda here is the decay rate. It's 1 over tau. Tau is the lifetime, related to the half-life. So the decay rate, the half-life, they're just inversely related to each other. That's the famous law of exponential decay. Equation 3 gives us the relation of lambda to the decay time of the particle. Notice if we take the derivative of n of t as a function of time, dn by dt, we get minus lambda n of 0. The lambda comes down from here. We get n of 0 times e to the minus lambda t, which is just the number of particles. Or we get the number of the particles decaying in time at time 0 times e to the minus lambda t. So as you see in the simulation, and you will see, I hope, the number of particles decaying as a function of time is proportional to the decay rate, delta n delta t. Okay. So the activity, which is the instantaneous rate, is a function of time. Lambda is the decay rate for any one particle. Okay, so that's a constant. But for the whole bunch, it's this number. So don't get confused. So go to the lab. Prove to yourself that exponential decay occurs as an approximation to the simulation. And see if this agrees with nature. Change the rates, run the simulation, do the experiments. You don't have to have your clothes washed afterwards because they may be radioactive, or test yourself with a Geiger counter. It's perfectly clean. So enjoy it. Be spontaneous in life. Enjoy the computers. Bye-bye.